Hello everyone, this is Katsuaki Suganuma from Osaka University. Thank you for inviting me to make this presentation. It is my great pleasure and great honor to introduce our latest research on Sinter joining and its summer performance. Uh, First, this is showing the outline of today's talk. First, I am going through the research background very quickly, then introduce silver sinter joining, our technology. Then the new bonding onto dissimilar materials, bonding capabilities. The final part is the thermal property evaluation and silver sinter joining capability. Then summary. Okay. First of all, I would like to introduce my laboratory briefly. So F3D stands for my laboratory name, very long name actually, Flexible 3D System Integration. Simply F3D is the name. We are working on interconnection, various kind of materials, soldering of course, and silver copper sinter joining, and ceramics metal joining, and adhesive bonding. These are for power packaging currently, and also post 5G, AI, IoT, advanced semiconductors. And performance and the reliability, especially thermal management, is today's topics. So I'm going to focus on silver sinter joining and thermal management today. As you know, there are so many products, silicon carbide and gallium nitride in the market worldwide. The hottest part is electric vehicle or hybrid or SUV, a big market. This is Chinese large bus with silicon carbide. And the mass production of silicon carbide vehicles started from America, so it is very famous. Tesla installed silicon carbide. And Toyota and Denso, they worked on hybrid vehicles for many years, and they showed large IGBT becomes very small. Sometimes the size becomes 1/5. So this is a great benefit for moving objects like these. So lightweight and size reduction makes many benefits. Of course, silicon carbide provides more than 70% energy loss reduction. This is quite attractive feature. In Japan, in Tokyo or Osaka, you can see silicon carbide equipped trains. And all bullet train, so-called Shinkansen, new one, is equipped with silicon carbide power module. Again, the size reduction benefit is very huge for trains. Like this, silicon carbide is opening the market already. And now we are looking at, of course, electric vehicle is a huge market it has. So this is one of the biggest one. But now we also talking about flying objects like drones, big drones, small drones, and even bigger electric planes will appear after 2030. For that, we need increase the power of silicon carbide power module, and also we have to think about lightweight. So this is our target: very severe power density and very high temperatures. For that, the key technology, one of the key technology is interconnection materials and also the thermal management because we need the cooling light. So, and also not only power modules, there another big market, AI, IoT, semiconductor, advanced semiconductors. And this has actually, this is market growth for two types. Fan-out high-level package is now growing. We are here now and growing rapidly towards 2030. And like this, we have to think about this market. One of the big issue for advanced semiconductor is again the thermal management. So by increasing the density of advanced packages, the computing speed increases rapidly like a blue line. We are expecting this blue line, but this is the maximum state. We have to think about density increase. That means heat generated inside silicon becomes much severer. If we don't make any further cooling technology for that, CPU throughput will saturate far below the maximum expected speed like this. So it is very disappointing. So we to improve this state, we have to make better, much better cooling technology and materials. Like this, so now computing becomes monolithic to chiplet structure, and now we are talking about 3D integration. This is showing schematic we are looking at. So 3D stacking of CPU, GPU, and memories, or some other devices inside high density packages. We have to think of the cooling materials or cooling method. So, for example, this is one example. In my laboratory, we are working on this. And of course, we are working on the bonding, kappa-kappa bonding, low temperature bonding is the other big issues. But as I told you, so thermal management it will become one of the key issues. And the other big subject for the packaging is the substrate side. Well, not only a substrate, maybe a silicon interposer will become substrate, organic interposer. Then we have to think about a fine pitch interconnection inside the substrate. One of the weakest point is microbarrier. So there are big issue on weak microbarrier. So we are also working on this. But today I'm going to focus on silver sinter joining low temperature. Okay, first I would like to compare the interconnection materials from solder, conductive or adhesive, and sinter joining new technologies, nano and some micron or microns. So the conclusion from my laboratory is a submicron. This is the best choice for future. Electric and thermal conductivity, solder is not ideal materials. And conductive adhesive, unfortunately, they are worse than solders. Copper or silver materials, they are the best choice talking about electric and thermal conductivity. And the strength, yeah, almost the same or much better for sinter joining. Heat resistance much better for sinter joining. IMC formation, this influence reliability of interconnection. Solder is the worst. Conductor adhesive and other sinter materials, they have no problem basically. Talking about the cost, of course, solder is the best choice, easy handling, but somewhat higher temperature. This may be problem. Conductor adhesive cost is it depends on silver price, but not so expensive. They are now using in the market already, and the temperature is very low. This is a good property. And nanomaterials cost is too high. Even copper, the cost is too high. So I don't recommend this one. And sometimes these material requires high pressure and high temperature. But silver and copper sub-micron or micron paste, the cost is not so expensive, much lower than nanomaterials. Copper is one of the best choice, talking about the cost. No pressure and low pressure, this is good property, and lower temperature than nanomaterials. So quite attractive, these some micron sinter joining technology. So we worked on silver, why we can make a good joints even at very low temperature like 180 degrees C at this moment, and very low applied pressure below 1 megapascal or sometimes zero in the atmosphere. So this is these are starting materials, so very large and sub-micron. And we got this microstructure, microporous silver layer. This has a very high strength, heat resistant, and high thermal conductivity, very stable. And even at 180 degrees C, we can get this microstructure. So that was a good big question, why we can get this kind of sintering networks. Finally, we got a conclusion. So this mechanism is so-called nanovolcanic reaction. Silver is interesting material. Silver absorbs oxygen along grain boundaries. And oxygen in grain boundary forms silver or liquid. So this becomes liquid. And under stress, some stress, this liquid comes onto the surface, forming amorphous layer first. Immediately it turns into nanomaterials, silver, pure silver nanomaterials, and promotes sintering. This is a mechanism, sintering mechanism at low temperature. So because of this specific reaction mechanism, we can get a good bonding. The feature of silver paste, so handling easiness, it can be the paste easily, and low temperature like 180 degrees C, no pressure sometimes, or only under very low pressure. Air atmosphere is okay, and high performance, heat and thermal conductivity is one of the best, and the reliability is very good. And because very low pressure or no pressure, large area bonding can be easily performed, and affordability. So many benefits from silver. I'm showing high temperature stability of silver sinter joint assembly. So in this case, gallium nitride is bonded onto DBC, and high temperature exposure at 250 degrees C, very high temperature, up to 1000 hours. No degradation from the initial, some changes but after 1000 hours, it maintains the initial strength like this. So great advantage compared to the other materials. And heat shock from minus 50 to 250 degrees C, very severe heat shock test. So initial strength can be maintained even after 1000 cycles. Like this, there is no serious degradation by using silver sinter joining. And also, we surprised solvent has big effect on bonding. Not only a silver to silver, we can perform silver to other materials. Uh, this is bonding strength on silver to silver without solvent. We have solvent, very simple ethylene glycol, and the small amount of addition of this solvent into ethylene glycol, the strengths jump up like this. At 180 degrees C, this becomes 3 times higher, and 200, of course, higher, like this. So solvent increases sintering capability from this microstructure to this microstructure at 200 degrees C. So not only a silver material, so solvent can modify the bonding capability. This is showing one example. Okay, then metallization. Solvent can improve the bonding capability onto gold, but the best choice is silver, and the silver sputter films on device or substrate is the best choice. So it maintains high strength at 250 degrees C again. 1000 hours, no degradation. This is showing yellow circle showing plating, electroplating silver. Then it can maintain very high strength even after 1000 hours, but slightly decrease like this. Gold, talking about gold finish, very thin gold though. So it has good strength initially and slightly decreased like this. Still more than 10 megapascal after 1000. This is not bad. But the best choice is silver spattered film. But lately we found much better choice. So sputtering becomes somewhat expensive. So all plating, many others we tested. Among them, we found some types of plating material like a cobalt tungsten or cobalt. They are better, even better than silver, like this. So this is showing initial strength. And so this is one of the best choice we tested. So very not so expensive like a silver or gold. Okay, now this is new challenges. Direct bonding onto dissimilar materials. So this is showing silicon carbide die attached onto DBA device structure with silver sinter materials. And DBA aluminum surface, there is no metallization. Usually, DBA, we have to make nickel plating on it for soldering. Otherwise, we cannot make joints. But without any metallization, we can make direct bonding silver sinter materials. And strength, shear strength, even at 180 degrees C, we can get some strength, almost 20. This is not so bad. But beyond 200 degrees C, so strength reaches 35 megapascal. This is good news. We don't need to increase the temperature, so 200 degrees C is one of the best choice. And it is very strange. So we can make a good joints, good bonding onto aluminum. Aluminum always has oxide on its surface. So this is showing a TEM cross section, and that actually there is very thin, like a 10 nanometer aluminum oxide amorphous. This is usual surface microstructure, and silver directly attached onto aluminum oxide. This is a strength. This can provide the strength to the joints. So silver directly bonded onto oxide surface. And the other material, we have tested many materials, silicon carbide, gallium nitride, like this. And silicon has this strength, very high strength. Silicon carbide, again, it's very high. And the gallium nitride, we don't need any metallization by using silver. So this is the interface. Of course, there is no reaction, no intermetallic compounds between two materials. And this is showing in TM, nothing there, but silicon has always a passivation layer like this, very thin, like a 1 nanometer or 2 nanometer maybe. So again, in this case, silver is bonded onto silica layer, amorphous layer. So very interesting. Now, final part, I come to thermal management. As in introduction, I explained about how thermal management becomes the key technology. So I'm showing here the schematic of silicon carbide power module, silicon carbide, and much heat from the top, sometimes 250 degrees C. Then it has to go through the vertically, and also we need horizontal uh, heat flux like this. And we have to understand all materials thermal conductivity and all interface heat transfer coefficient. Otherwise, we cannot design the best properties for the device. Talking about thermal performance, one of good parameter is thermal resistance. So it's easily expressed like this: from the top to the cooling plate. All resistance, thermal resistance can be added, and we get this total thermal resistance. So to understand thermal performance, we have to measure the thermal properties, thermal conductivity, thermal interface transfer coefficient, and especially thermal resistance of device. This project is funded by government, and the standardization committee is formed under the Japan Fine Ceramics Association. And we formed 3 groups like this, and each group trying to establish new method, accurate methods for thermal properties of devices. From this group, very simple thermal resistant measurement method come out. And this is it. So very simple thermal. Here is the computers and power source, and here is the sample. And this is a picture testing our demonstration module. You can see a heat sink. And this is showing the schematic. Very simple. So silicon carbide, and in this case, we use the DBA, aluminum boss face, and aluminum heat sink. This is one of the typical structure. And we change the die attach material, silver and solder, and TIM between DBA and aluminum heat sink. We changed the material from silver sinter materials, solders, and grease. This is a typical TIM. And we measure the total thermal resistance by using this setup. And the result is very simple. So we changed the interface materials, and this is actual structure. As you see, aluminum heat sink, usually it has very complex like this, so we cannot apply a high pressure to make this assembly. So we don't apply the high pressure actually. And the result is shown here. So this is showing silicon carbide top temperature change as a function of time. We put the same power onto the silicon carbide. Then look at blue line. It increases immediately in 2 seconds or 3 seconds. It reaches to 70 degrees C, very high temperature. We have to think about this one. So this is solder conventional bonding or TIM materials, solder grease. Then please compare this line with this one. So all silver sinter joint die attach, and also the bottom face is bonded by silver materials, because our silver materials can bond pure aluminum. And this case, as you see, temperature increases immediately, and after 2 seconds, it reaches about 180, just below 180 degrees C. This is the maximum temperature. So the same power, but we can keep the silicon carbide very cool, 100 lower than the conventional assembly structure. So this is our latest results showing great performance of silver sinter materials. Okay, here comes the summary. I showed the property of silver sinter materials we have developed, and it provides great heat dissipation capability, not only the strength and the reliability. And the good news is silver sinter material can be bonded onto many substrate or devices directly without any metallization. And the simple thermal property measurement method made a great demonstration of the capability of cooling the silicon carbide device. Okay, thank you very much for your kind attentions. Questions are welcome and at this email address. And I would like to acknowledge all those support from the companies and government funding projects. Thank you very much.